Krishnan and Adrian Veta. And the slides are made by Prasanna, and I'm borrowing his very nice slides. So the topic is how to keep the majority on your side. And the talk will be about elections. And in a classical setting, in elections, we consider the voters to have ranked preferences over the candidates. For example, throughout this talk, you will see a lot of these matrices where each column is the preference of a voter. And we list the candidates in this column where the candidate in the top row is the first choice of that particular voter. And the candidate in the bottom row is the last choice of that voter. For example, if we look at the first column, then that represents the preference of voter number 1. For example, he will think that the first choice of him is candidate number 4. And also he likes candidate number 5, the second best, and so on, until he likes the candidate number 2, the worst. And a central question in social choice theory is how should we choose the best candidate in some sense? So that might be the most important question in social choice theory. And I just want to quickly argue that elections are actually everywhere. So when we heard the term elections, maybe we first think about the political elections, where the voters cast their votes to elect political candidates. However, elections are also happening outside the political world. For example, when a hiring committee is deciding which candidate to hire, then maybe each person on the hiring committee can cast some vote, and together they can decide which candidate to hire. And maybe when some judges are deciding which candidate can win some award or some fellowship, maybe those judges can each cast some vote, and then they run a voting mechanism and get some winner. And in everyday scenarios, there can also be elections. For example, my co-author Prasanna like to use voting rolls to decide where to eat or which board game to play. So in those scenarios, we can also view these things as elections. And very recently, there has been some connection discovered between social choice theory and artificial intelligence. For example, just in the last year, there has been many work, including the ones I listed here, that argue for the use of social choice theory on the alignment of AI, the alignment of large language models. So the idea is in those processes, we often ask for people's feedback on the output of large language models. And different persons have different perspectives, and they can have different opinions. And therefore, when ultimately we want to aggregate those preferences into some social preference, we can use some voting role to do that. So there has been some connections discovered between social choice theory and the AI. And let's go back to our question, how do we choose the most broadly appealing candidate? So if there are only 2 candidates, then maybe the most natural way to do this is just to use the majority rule. Let's say there are just 2 candidates, maybe the only reasonable way is to pick the candidate that has the majority support, right? So if there are 2 candidates, A and B, if A gets more than 50% of the vote over B, then probably we should pick A in this scenario. And in general, if there are more than 2 candidates, we can still argue for the same thing. So if a majority of voters prefers a candidate A over another candidate B, then probably we shouldn't choose this candidate B over A, right? That seems a natural criteria that we want to satisfy. However, that idea will run into Condorcet's paradox, which was proposed by Nicolas de Condorcet in 1785. So he pointed out that it is possible in some elections that no matter which winner we choose, a majority of voters will prefer another candidate. Okay. And the simplest example for that is just this example with 3 voters and 3 candidates. It's kind of a cyclic preference scenario. where voter one likes candidate one the best, and then candidate two the second best, and candidate three the third best. In this case, let's say hypothetically, if we pick candidate one as the winner, then we realize that a majority of voters, in fact, 2/3 of the voters, will prefer this candidate three over candidate one. Right? And similarly, if we pick candidate three as the winner, then two will have majority support over three. And if we pick two as the winner, then one will have majority support over three. So the idea is no matter which winner we pick, a majority of the voters will prefer some alternative over the one that we have picked. And in fact, the Condorcet's paradox can get even worse. So we realize that it is possible that no matter which winner we pick, almost every voter can prefer some other alternative over the one that we have just picked. For example, we can just expand the previous counterexample with more voters and candidates. Let's say hypothetically, if we pick any candidate like 5, then we realize that this candidate just above it, number 4, can get 90% of the support in this case over 5. So the idea is no matter which winner we pick, 99% of voters can prefer some other alternative over the one that we pick. So that's an unsettling possibility. So no matter who wins, we are living with a mob of unhappy voters. So what can we do in this scenario? And as computer scientists, we need to relax the notion, right? And one particular idea is what if we allow multiple winners to win the election? So instead of electing one candidate as the winner, we are electing multiple winners. And typically in the literature, the idea of electing multiple winners is called committee selection. So the set of winners is called a committee. For example, in this instance, suppose we elect two winners, candidate number 5 and candidate number 10. Then we realize that we actually are avoiding the Condorcet's paradox, because if we are electing 5 and 10, then the best thing that the adversary can do is to pick someone like candidate number 4, and 4 only has 40% support against this committee consisting of 5 and 10. So in this case, if we pick two winners, we can actually avoid Condorcet's paradox. And you may think electing multiple winners in an election is pretty unreal. For example, in a presidential election, we can't really elect two presidents. But I want to argue that in some scenarios, it's pretty natural to elect multiple winners. For example, in grant or fellowship selections, we can award the grants or fellowships to multiple applicants. And for example, in hiring scenarios, we can also simultaneously make multiple hires. And when ordering food, we can order multiple dishes. And also for this voting to elect representatives for some district, there are some mechanisms that are multi-winner elections. And also, even in the US, there has been some proposals to change from the single winner election into multi-winner elections, where we want to have larger districts, but have multiple winners for each district, so that the overall representation can be more proportional to the actual support. And even in cases where we ultimately want to elect one winner, we can view this committee selection as a pruning step to select a small subset or finalists of the candidates. For example, in awards, maybe there are nominees, and in hiring scenarios, we want to interview multiple people, so there are interviewees. And in political elections, maybe we want to hold primaries first, and then the winners in the primaries can enter the next stage. So we can also view committee selection as a pruning step in single winner elections. Okay, let's go back to the technical problem. Condorcet's paradox said that it's possible that no matter which winner we picked, a majority of voters can prefer some other alternative over the one that we have just picked. And in 2011, there was a paper by Elkind, Long, and Safieddine. They proposed the notion of Condorcet winning sets. The idea is, can we choose K winners such that less than 50% of voters prefer any alternative candidate? Okay, can we choose K winners such that for any alternative candidate, less than 50% of voters will prefer this alternative candidate over the committee of K winners that we have just picked. So that's a single candidate. So that means we want to select K winners, and we want to compare against one single candidate. So the quantifiers are, we want to argue that there exists a set of K winners, so that for any candidate that we didn't select, at least 50% of voters prefer the one that the committee that we selected over this one candidate that we did not select. Is that clear? Oh, right. That's a great question. So each voter will view a committee as the best candidate in that committee. So, right, exactly. Is the question clear? And for this problem, we quickly see that if we just pick everyone into the committee, okay, we pick every candidate into the committee, then obviously it trivially satisfies this condition because there are no alternative candidates. So the question is, what is the smallest k such that we can always pick k winners such that less than 50% of voters prefer any alternative candidate? In practice, we can't just announce every candidate as a winner. We want to limit the number of winners that we can announce. And more generally, this 50% can be changed to some parameter alpha. And so we can also phrase our question as, for each k, what's the best alpha that we can guarantee? For example, if we are allowed to pick two winners, then can we guarantee, for example, less than 80% of the voters can prefer any alternative candidate? So that's the question that Elkind, Long, and Safieddine considered. The notion is called Condorcet winning sets. So the set of K winners is a Condorcet winning set. And I feel the question is pretty interesting in the sense that it's an 18th century question in some sense. So even though Condorcet himself may not have posed this question, it feels like a question that could have been posed by Condorcet. It's really natural and basic. But in our work, we will tackle it with modern tools that were not available to Condorcet. We will formulate the problem in game theory jargon, and then use the probabilistic method to prove the existence of a Condorcet winning set. And this work builds on some recent work on approximately stable committee selection, also called the approximate core in committee selection settings. It's a work of our prior work. So let's briefly describe the status prior to our work. The question is, can we choose K winners such that less than 50% of voters prefer any alternative candidate? So in 1785, Condorcet pointed out that when K is equal to 1, it's impossible to have such a guarantee. And then when in 2011, Elkind, Long, and Safieddine proposed this notion of Condorcet winning set, they gave a lower bound that said 2 winners is not sufficient to guarantee such a thing. So let's describe their counterexample now. The idea is to multiply a 3 cycle and a larger cycle. So we group the candidates into 3 blocks, 1, 2, and 3. And we have equal number of voters and candidates. In this picture, it's 15 voters and 15 candidates, like this. And then each block consists of many candidates. In this case, it's 5 candidates. So we unwrap each block into 5 candidates like this. And then we want to argue that if we are only allowed to select 2 candidates, then it's not enough to guarantee a majority support of voters. There are 2 cases. One case is we pick 2 candidates that are in the same block. Then, for example, we pick 3 and 5. They're really the same thing. We pick any 2 candidates in the same block. Then we realize that the adversary can pick some candidate in the previous block, and that candidate will win 2/3 of the support against the 2 candidates that we just picked. So it's not good to pick 2 candidates in the same block. And the other case is to pick 2 candidates in different blocks. And it's also kind of the same thing. If we, for example, pick 5 and 10, then we realize that the adversary can pick some candidates in the same block as one of the candidates that is just above that particular candidate. So if we pick 5 and 10, the adversary can pick 4 in this case, and that will get almost 2/3 of the support against our committee. So that showed if we can only pick 2 candidates, then we can't do better than 2/3, right? We can only guarantee 1/3 of the support. And more generally, if we can pick K winners in this scenario, then there is some alternative that is preferred by 2 over K plus 1 minus epsilon fraction of voters. So if K is equal to 2, then the adversary can get 2/3 of the support. And if K is 3, then maybe it's possible that we can guarantee majority support. So that's the lower bound that they have. And for the upper bound side, and by the way, there are actually also many other counterexamples. There are people from different communities trying to get counterexamples for this for the condensate miniset notion. And one particular direction is to minimize the number of voters and candidates so that 2 candidates are not enough to guarantee this thing. I think there's some unpublished work showing that we can have 7 voters and 7 candidates, showing that 2 winners are not enough to guarantee it. And on the upper bound side, in the original work, they showed that it's enough to pick log m candidates to guarantee such a thing, where m is the number of candidates in the election. And the algorithm is also pretty simple. We realize that for any pair of candidates A and B, either A can get majority support against B, or B can get majority support against A. Right? So on average, every candidate can win against half of the other candidates in pairwise comparisons. And therefore, if we pick the candidate with the most pairwise wins, then that candidate will win against at least half of other candidates. So if we draw a picture like this, if we pick the point on the bottom, then that candidate will win against some other candidates and lose against some other candidates. But if we pick that winner into our set, then we can eliminate everything that it can dominate. And therefore, we only need to recurse in the remaining set where it's not dominated by this particular winner. So in each step, we reduce the size of the set by a factor of 2 at least. And so it's sufficient to pick log m winners to guarantee majority support. So that's their upper bound of log m. And that's the question, is the answer log m, or is it more like a constant? And in our work, we showed that in any election, we can always pick at most 6 winners, such that less than 50% of voters will prefer any alternative candidate. So there's always a condensate meaning set of sets at most 6 in any election. And in fact, the title of our paper is 6 candidates suffice to win a voter majority. And so we pointed out that we can change this 50% to some parameter. And more generally, our result is we can choose at most K winners such that less than alpha fraction of voters prefer any alternative if this inequality holds. And maybe that inequality is not that easy to parse, but we realize that the lower bound is alpha less than 2 over k plus 1. So when alpha is less than this, it may not be possible. So our bound is alpha over 1 minus log alpha larger than the same thing. So essentially, we lose a factor of 1 minus log alpha in this guarantee. So that's our result. And if we plot the upper bounds and lower bounds in this graph, the lower bounds was given by the original work, and the upper bounds are in our work. We can see there's some gap, but it seems to be a reasonable approximation to the lower bound. And in particular, we showed that even if we can only pick 2 candidates, the guarantee is already 80%. So that means there's always a set of 2 candidates, so that for any other candidate, the fraction of voters who prefer these 2 candidates over that 1 candidate is at least 20%. And that seems to be novel to the best of our knowledge to get anything better than like bounded away from 0. Even for k equals 2, we are not aware of any simple proof for this fact. It seems like a really simple combinatorial statement, but it seems not very easy to prove actually. And our threshold for majority support is 6, meaning that when k is 6, this curve drops below half. And one interesting thing is that nowadays, the Oscar Best Picture have 10 nominees. And back in 2010 or before that, the Oscar Best Picture only had 5 nominees. So why did that happen? It turns out that in 2009, some movies that are considered good by the public did not get nominated. Maybe then the award committee realized that it's easier to satisfy this Condorcet winning set condition if we increase the number of nominees. And before we go to the proof, let's have some digression for it, a fun digression. So let's say here's the dice game. There are 4 different dice. I actually brought a set of physical dice here, but I don't know how to like actually play it with the audience. Yeah, so there are 4 dice. The first die have 3 on each side, and the second die has 4 on 4 sides and 0 on 2 sides. And then there's a die with 4 2s and 2 6s, and the last die has 3 5s and 3 1s. The game goes like this. We each pick a die and roll, and the person with higher roll wins the game. Okay, so that's the game. And let's say if I'm being nice and allow you to pick first, then which die should I pick? Any volunteer to pick some die here? The green one. The green one is 5 5 5 1 1 1. That seems to be a great choice. Let's try picking all 3s first because that's the animation. Let's say, for example, you pick the die with all 3s, then I will pick this die with 4 4s and 2 0s, and I can win against you 2/3 of the time. Because if I roll a 4, then I will win. So I can win 2/3 of the time. So the die with all 3s doesn't seem to be very good. Then maybe you want to say, let's pick this die with 4 4s and 2 0s, but then it will be beaten by this 3 1s and 3 5s with probably 2/3. To see it, if I get a 5 in the green dice, then I already win. And if I roll a 1, then I can still win with probably 1/3. So the overall winning probability is 2/3. And then if I pick the green die, then it's probably better to pick the purple die against it. And the winning probability is also 2/3 by the same argument. So if I roll a 1 in the green die, then I already lost. And if I roll a 5, I still lose with probably 1/3. So the overall losing probability is 2/3. So the purple die will win with probably at least 2/3. And similarly, if I choose the purple die, then the blue die can win against it with probably 2/3. Because if I roll a 2 in the purple die, then I lost. So there's actually a cycle in this game. No matter which die you pick, I can pick a different die that can win against you with property 2/3. And such a phenomenon is called the non-transitive dice or intransitive dice in the literature. And it's actually an interesting object that many mathematicians have considered. For example, there has been a polymath project about intransitive dice. And also it's a popular topic in popular math, where mathematicians try to introduce this notion of intransitive random variables to the public. And there's also an interesting anecdote that Warren Buffett seemed to be a fan of intransitive dice. And there was a time that he was trying to trick Bill Gates with this game. So he was saying, I'm so nice, so you get first pick. But then Bill Gates examined the dice for a few minutes and say, no, you first. That's an interesting anecdote about the dice game, the intransitive dice game. And how is it related to our topic? So this intransitive dice itself is rigged against the first chooser. We want to slightly change this game so that the game seems more fair, right? And one way to do it is to give the first chooser a leg up. Let's say we allow the first chooser to pick multiple dice and then take the best roll. So the first chooser maybe pick these two dice and roll them, and then pick the best number on them. So in this case, can we still have the same phenomenon? Can the game still be rigged if the first chooser can pick, let's say, 10 dice? And then we realized that this problem is actually just voting in disguise. We can view the dice as candidates. And the points in sample space are the voters. And then the order in sample is the preferences. For example, if we roll these dice and get 3, 0, 2, and 5, then we can have a voter who thinks this green die is the best, and then 3, this blue die is the second best, and then purple, and then orange. Right? We can have a voter that represents every point in the sample space. And then we realize that if every die loses to another die with probability more than half, then that means for any candidate, a majority of voters will prefer another candidate. And therefore, the non-transitive dice are a particular example of the Condorcet paradox. Even though it's not the easiest counterexample, it's one counterexample of Condorcet's paradox that states that the social preference can be intransitive. And if we rephrase our result in the dice world, then we can say that with any arbitrary dice, with an arbitrary set of dice, even if they can be arbitrarily correlated, 6 dice is always enough for an advantage. So the first player can always pick 6 dice to guarantee a more than half probability to win against the second player. So that's our result in this dice world. Oh, that's a great question. So I don't know if I'm not aware of any published work on it. And in kind of ongoing work, we are trying to consider a case where the dice are independent. And I think for 3 dice, it should be enough for the first player to get an advantage, and it's not clear whether 2 dice are enough. So we think 3 is probably enough because 2 is very close already. We were trying to see whether 2 dice are enough. But that is the correct answer. The answer seems to be very close to 2. So even if 2 is not enough, the fraction, the winning probability should be very close to half. So it's not that easy to figure out whether 2 is enough or not. Okay. And then let's move on to the proof of the result. So our proof can be roughly decomposed into 3 parts. So the first stage is to consider some existing work on game theory and this social trust literature. And the idea is if we can have randomness, then the problem will be vastly simplified. I will go into that later. And the second stage is to create a measuring stick, a way to compare voters, to compare candidates and committees against this measuring stick instead of comparing candidates versus committees themselves. We want to have some measure on the qualities of candidates and committees. So that's the second stage of the proof. And then in the third stage, we want to measure a random committee and then to argue that there is some committee that's pretty good, and so it can beat every single candidate. Okay, so the proof will go like this. So let's first look at the first stage. We consider randomness. So recall, this is the lower bound that we had. And suppose we can actually match the lower bound, then our result will be this. There is always a committee S of size K, such that for any alternative A, at most 2 over K plus 1 fractional voters should prefer A over S. So if we write it down in formula, then it means there exists some committee S, such that for any candidate A, the fraction of voters who likes this candidate A over the committee S should be less than 2 over K plus 1. Okay. That's the thing that we ideally want to prove. One question is, what if we can randomize? And then it turns out that there's a notion called stable lotteries in literature that's very helpful. So if we can actually randomize over this committee S, then there is some randomized committee delta, such that for any candidate A, if we draw a random committee from this distribution, then the expectation of this amount, the fraction of voters who like A over S, is actually at most 1 over K plus 1. It's even a factor of 2 better than the best we can hope without randomization. Okay, so that's actually known in the literature. If we can randomize, then we can actually have a guarantee of 1 over K plus 1. So why is this true? I'm copying the same thing here. And the proof is actually very easy. It's just an application of the minimax theorem. So here's the game. Okay, I choose the distribution over committees, and then you choose a single candidate. Okay, and then I draw a committee from my lottery, and the voters will compare. Because of the minimax theorem, it's the same as saying you first choose a distribution over candidates, and then I choose a single committee, and then you can realize the draw, and then we compare. Okay. But then we realize that I'm free to choose this committee depending on your lottery, on your distribution over the candidates. So what I can do is to just sample K times from your lottery, IID. And then we realize that I'm sampling from the same distribution K times IID, and you have one sample from the distribution. So I should win with probability K over K plus 1, and you can only win with probability 1 over K plus 1. So that means the value of the game should be 1 over K plus 1. And therefore, we have this statement. If we can randomize, we can actually guarantee 1 over K plus 1. Uh-huh. Depending on the I realize this I didn't. You mean like in the original game? Could be. I first formulated the original game and then realized using the minimax theorem to consider the dual of it. And then no matter which distribution you pick, I can sample from the same distribution K times IID. Let's say if your randomized strategy is to pick 1 with probability half, 2 with probability half, I can just sample from the same distribution K times. And I argue that if I do that, I win with probability K over K plus 1. Yeah. We can consider them to be overlapping as well. That doesn't matter. Yeah, thanks for the explanation. So that's the first thing that we can realize. And then in the second step, we want to create a measuring stick, some way to measure the quality of candidates and committees. So to do that, we can draw a picture like this. We want to visualize all the committees and preferences in this way. So each column represents a voter. And then each committee is a block in the column. And the height of the block in the column is the probability mass of the committee in this stable lottery distribution. Delta is the thing that we just constructed before. And the order is the same as the voter V's preference order in this sense. So if she ranks the four committees in this way, she will put the committee S at the top, and then the orange committee, and then the blue committee, and then the purple committee. And then we can put candidates to be somewhere between the blocks. So if we put candidate A here into that position, then it means that this voter V thinks the candidate A is worse than the orange committee, but is better than the blue committee. So we can visualize this thing like this. And the key is V prefers A over all in S, if and only if A sits above S in V's column. Okay, so for example, for this voter V, he thinks the committee S is better than A, so that doesn't satisfy this condition. But for another voter V, she puts A above S, so she thinks A is better than S. And the idea is to argue that all the candidates are low in this picture, and also some committee is high in the picture, so that it's impossible that more than half of the voters prefer this candidate over the committee. Right? So the idea is for every candidate A in this picture should be relatively low. And there exists some committee as the shape of the committee S should be relatively high in this picture. And therefore, it's impossible that more than half of the voters prefer A over S. So that's the structure of the proof. Okay, let's first look at the first thing. We want to argue that all candidates are low. So that's actually just the property of the stable lotteries. So because of our construction of the stable lotteries, we know that for any candidate A, the probability that A can beat a random draw from this lottery is at most 1 over k plus 1. And that actually just means the average height of A in this picture should be at most 1 over k plus 1. And the height is just the expected fraction of voters that prefer A over the random draw from this lottery delta. And next, we want to show that some committee is high for most of voters. Okay, and for example, if the committee looks like this, we can just sort the voters according to the height of S. And then we look at the area of half of the voters that rank as the lowest. So if some candidate A wants to beat S for more than half of the voters, then the area below A should be at least the area that looks like this. And we want to argue that there is some committee S whose area here is larger than 1 over k plus 1. So for any candidate A cannot possibly beat S according to half of the voters. So that's the idea. We want to show that there is some committee that is high enough if we view the committee in this way. So the question is, how do we find such a high committee? And the idea is also quite natural. It's just to randomly sample this committee from the stable lottery. And we argue that the probability of success is actually pretty high. So the intuition is to each voter, if we sample a random committee, then the height of the committee for that random voter, for that voter, is just uniform 0, 1 distribution. And if everything is independent, then the overall shape should be pretty close to just a uniform distribution. And if we sample many points from uniform 0, 1 at random, IID at random, then the overall shape should be roughly this y equals x line. However, things are not that nice because there's some correlation between committees. And therefore, the argument doesn't quite go through, but hopefully it's pretty natural that the average height of the committee is still pretty high. And therefore, there is some committee whose shape isn't much worse than this. So if we just pretend that this argument works, then we can say there's some committee whose shape is like this, and therefore the area below the bottom half is 1/8, and therefore that can prove that if we select 7 candidates, then it should be enough. However, there's some problem with this independence assumption, but that can actually be bypassed with some arguments about, like, we can, for example, do case analysis for it to prove it. And in the paper, we also have some other ideas to improve this constant to 6. So we show that 6 candidates are always enough to guarantee majority support. So that's the proof overview of our result. And I want to quickly mention some extension in one ongoing work. So in this talk, I talk about this condensate meaning set, which states that we can always choose 6 winners, such that for any alternative candidate, these winners together can win at least 50% of the votes against this alternative candidate. So that's the result I just presented. And in ongoing work with Moses Charkar and Prasanna Ramakrishnan, we consider the variant of this problem. So we showed that we can still choose a constant number of voters, such that for any alternative candidate, one of the chosen winners can win at least 49% of votes against this alternative candidate. We can still select a constant number of winners, such that for any alternative candidate, there is some chosen winner that can win at least 49% of the votes against this alternative candidate. So in the original thing that we talked in this talk, we are considering these selected winners together. So each winner can maybe dominate different group of voters. But in this new notion, we showed that even if after the adversary picked this candidate, we only need to select one winner, and we can still guarantee at least 49% of votes against the candidate that the adversary selected. So maybe the surprising thing is, even in the stronger notion, it's still sufficient to only select a constant number of candidates. Oh, that's actually true. Yes, you can get it. If you can assign different ways to the things that you selected in the committee, then it's true. Oh, right. Yes. So we can't guarantee 50% with a constant set support. Maybe so there's the same log m lower bound. For if we want to guarantee 50%, we need to select log m candidates where m is the number of candidates. But if there's a constant gap, if we only want 49%, then we only need to select a constant number of winners. Or a different way to say this is we only select one winner, but it can be randomized. And the guarantee is for any alternative candidate, in expectation, the thing that we selected can win at least 49% of the votes against this alternative candidate. And the point is our randomization only need to have constant support size. So that's another way to phrase this. Mhm. Oh, right. That's a great question. So if this 49% is 50% minus epsilon, then the set should be big O of 1 over epsilon squared. The point is it doesn't depend on, it doesn't need to depend on the number of voters on kind. Okay, so that's the technical part. And you may ask, why should we study elections? It's pretty hard to change, like, for example, the format of presidential elections. But we want to argue that there are many applications of elections other than just politics. For example, in hiring, in award selection, or just in everyday scenarios, we can use voting rolls to decide the outcome. And also another perspective is these elections are very interesting to study. They are fundamental mathematical objects about graphs and posets. And so Press said that it's very interesting, so we should understand everything that we can about them. And that's all I have today. The takeaways are committee selections can save us from condensate paradox. And to prove our result, we used notions from game theory and the probabilistic method. And there are many open problems in the space. For example, what's the correct number for the smallest condensate winning set? Is it more like 3 or more like 6? And also, what's the best guarantee if we can only pick 2 candidates? And also, is there a simple, efficient algorithm to select the committee instead of just relying on this random, this probabilistic argument? So that's all I have today. Thanks for having me. That's awesome. Mm-hmm. Just really say like this. It's not. Sorry. Yeah, as you said, found intuitive algorithm, right? So in this so this so like the point is the earlier arguments already depends on this dual view. So so in fact, I don't know like what the adversary will pick as her random strategy in the first step. So like my choice will actually depend on that. So it's unclear how to do it. That's what I think. So we don't know any like nice algorithm to find it. Like we can always just enumerate the subset of set 6 to get a polytime algorithm, but I don't know if there's any good algorithm. Right, it's easy to do this log and in a very short time. Uh-huh. Uh-huh. Already seems very surprising that uh-huh. Is there any idea that we can really why do stable lotteries exist? I don't know if that's very intuitive, but the rough idea is, I mean, you are free to pick one candidate. I'm free to pick k candidates. So by the minimax theorem, I can ask you to go first to use a randomized strategy, and then I can mimic your strategy k times, so that my winning probability should be k or k plus 1. So that's the proof. And I don't know if there's any intuitive idea to get it, or are you asking for something? Okay. Uh, I think so, yes. Like for some epsilon error, I think it can be implemented. Yeah, I think so. We can probably do it with some error. Yeah, that makes sense.
Well, that's some comment.
Thank you. Thank you.